With the Advantex subfloor assembly, you can be sure that you're building a reputation on something stronger. And the best builders, well, they may always stand apart, but they never stand alone. So ask yourself, are you bringing your A game?
Hey everybody, welcome back to Before the Build on the Unbuilded Podcast. So, today we start diving into some of the details. I mean, up to now, we go through 13 videos. They talk about elevations and floor plans and all of that stuff. But at some point, as an architect, you have to start thinking about, okay, how does this thing actually stand up? And what kind of materials do the contractors actually put their hands on? And how do they put it together? What are the dimensions? All that good stuff. How do we collaborate with the structural engineer? Whole bunch of stuff. So anyways, got Big Red in hand. Got the footing details right here. So let's not talk anymore. Let's dive in. All right. So broke out a couple of the details here from the foundation page of the set of drawings. Notice we have two cross sections through the footings. This is that more common one. That is just a big block. These are the intermediate ones. And then this one was, let's call it the special one, because this one, notice here, it has a seat. And that seat was certainly intentional. So there you have, and then we have that cold joint there, footing there. So footing design. I mean, as I talked about earlier in the foundation plan, footings are nothing more than the feet to the building, right? So the bigger the cross-sectional area is here, as the building pushes down here, the ground can resist. And that's what holds your building up, right? Well, like anything, if that area is only a foot deep by, say, 3 feet, then we have 3 square feet. If I make that 2 feet deep, then I have 6 square feet, and obviously 3 feet, then I have 9 square feet. And that 9 square feet, exponentially increases the bearing load that I can impose on the ground and get the resistance to hold it up. So the engineer obviously works all that out, and, we have a rough dimension, but these footings here ended up being 4'6" long and actually 30 inches in width. So I don't know what that is, probably about 10 square feet or so. So that's what's basically exerting, or the platform upon which we build up the building. Now, we don't need to do that whole 10 square feet all the way up to hold the building, just like our leg isn't the same size as our foot. The foot provides the stability for us, but it doesn't necessarily need to provide the strength to move up through our legs. So the foundation system, and in this case here, because there are these exposed piers, it is very much synonymous with our own body in that we have the foot down here, or footing, but we have the leg up here. And notice that the leg is significantly narrower, and it's narrower in width too here, that it's only like 10 inches wide, and the footing here is 30 inches wide. So it basically sits in the middle of that footing. So concrete works very well in compression. So as the building tries to exert a vertical load just because of its sheer weight, the foundation very easily pushes back. Doesn't have a problem there. Concrete works very good in compression. But where concrete doesn't work so well is in tension. And so we have to find some type of system that can handle the tensile forces in the foundation system and let the concrete handle the compression. So compression is easy, like we talked about, just concrete. You know, concrete from your experiences with it, I'm sure. You're not going to stand on it and your foot's going to go through it. It's not happening. But when you have a building like this, and if the leg is strong enough, then it comes down, well, this wants to bend, right? So as that force gets exerted and that footing wants to bend, we need to push back. And that bend or stretch is the tension that I'm speaking of. So how do we battle that? Well, you notice here we have a steel bar that goes in there, and then we have a few steel bars that go transversely through the footing, right? Those go all the way up, and then these go across this way. So it basically creates this matrix in the footing that's like this. So you have this steel net that is embedded inside that concrete footing, so that as that load comes down, footing tries to bend, that steel picks up for the slack that the concrete can't handle in tensile force, and it resists the bending by basically holding it together. Now, the other force that's happening here, well, there's a couple more. One, when the wind blows on the building and it tries to push it over, this wants to deform, right? Whether it's that way or this way, depending on which way the wind blows. How about that? So, again, easy. On the inside corner here, we have compression, but on the outside here, we have tension. So how do we deal with that? Well, just like we developed this horizontal net here, we develop a vertical matrix of bars here. And then those bars have horizontal bars that get attached to it, so that as it tries to bend, these steel bars pick up the tension forces that the concrete can't handle, and they basically piggyback the concrete in resisting that wind load when the building wants to shift left or right. Now, one of the other forces is a torsion force. What if the building wants to kind of rotate on that footing, meaning spin around, right? We have some forces there, these torsional forces that are at play there. Well, we have this series of stirrups here, and you can see at the top here where this is most susceptible, right, to that turning, because down here, not only are we anchored, but we're anchored into the footing. We don't have an anchor point there. So while we have stirrups going up here, these are very modestly spaced, but these are very tightly spaced. And the reason for that is that the top of this footing is the most freest to move, which means it has to have the most reinforcement in there to resist that turning force. So we kind of up our stirrup game. And the stirrup game is nothing more than, if we have these 6 bars, let's see if I can draw this here. These 6 bars that are going up through the footing, the stirrup basically goes around them and then gets tied off like that, right? So the stirrup is nothing more than kind of a belt to those vertical bars, and it makes these stirrups work in complement to the vertical bars, in complement to the concrete, so that the concrete handles all the compression forces, but the steel stirrups and vertical bars are handling those torsional forces inside there. So, I mean, I know everybody's seen reinforcing, but it's good to kind of run through what is that reinforcing actually doing inside that footing. Now, let's move over here, because over here we had the special footing. Notice, like I said, it has that step. And we have some bars there. We also have the bars here that are very similar to that. And notice that our stirrups are nice and tight up there. Then we have the modestly spaced stirrups down at the bottom. But notice here, we have this 8x8 steel column with a base plate. And then that has anchor bolts that are coming down into the concrete. And it is no surprise that those anchor bolts are coming down inside this cage of steel reinforcing, because this post here, if you remember in the elevations, that's where that cantilever deck comes into play there. And we wanted, oh, sorry, it's up here actually. And we wanted that cantilever deck to be pretty much the same level as the subfloor. So you just walked out. We stopped our decking just short, so there's a little space there. But this is thermally broken here from the structure to the deck. So the deck is somewhat, you could say, independent of the house itself. The only place it's connected here is, as my good buddy Mark Willie would say, it's the legend of 8 bolts. So 4 bolts per post. That's all that's holding that on. So this footing here, not only does it have to hold up the building here at the end of the house, you see the beam there that goes across to the other concrete pier, but we created this shelf because now this footing is also carrying the deck, but we had to drop this down so that we could coordinate the top of the decking with the top of that subfloor to have that transition of no delta in height there. And because of all of those forces acting in here with that, this thing wants to rotate physically, so it wants to rip these bolts off. So tying those into the anchor bolts into the concrete and likewise into this steel cage helps reinforce and hold all of this together to react against those overturning forces in how the deck wants to rotate. And then again, just like here, we have that series of rebar and that matrix that goes up, and these bars go in here, and then we have these bars here. So it's basically a steel mat down in the bottom of that footing to keep it from pushing through, right? So that any weight that gets exerted, we need the footing to push back. So anyways, that's board form concrete pier footings and what they're actually doing and how they're holding up the building. So hopefully you enjoyed that. Stick around. We got some really great photos to show you.